So let's say you want to use another method. For instance, you want to use trunk, which is also from JSO solvers. Again with the with logger. Trunk. So trunk runs and say hprod exclamation is not defined. Somewhere around here it uses hprod because it's trying to define, it's trying to use the Hessian because trunk is a second order method and that's not defined. So here I'm using trunk, I say please just run with a second order, and it says you don't have a second order function that I need, hprod exclamation mark. So I'm gonna define hprod exclamation mark. And hprod exclamation mark, where's my abstract? I just want to use tab. Hprod exclamation mark is a function that has an optional argument, which is the objective weight, in addition to being the Hessian at x times a vector v. So let's define this. Looking at this function, well, this function, you can see that the Hessian is also well separated, and you can look here the gradient to try to compute this in your mind, in your head, sorry. And what we have is that, sorry, I forgot to define the output. Not define, declare. So here, what we have for hv is that it's gonna use another derivative here of xi. So it's gonna differentiate this guy. It's gonna be a 2 plus, here I'm gonna have minus 400 alpha, and for that I'm gonna need alpha. And I'm also gonna differentiate alpha with respect to xi. So this is gonna be minus 2xi, with this minus gonna be plus 800 xi squared. Okay, so this is gonna be times vi, and I'm also gonna differentiate this. Is gonna be minus 400 xi times vi plus 1. Okay, so there's really no easy way of just using this. And 200 vi plus 1. Okay, so I could as well, well, this is not needed, but I could as well use vi and vi plus 1 to avoid accessing the vector, but this is just an example, so let's be wasteful. Again, return what you're modifying, in this case hv, and let's see if we made this correctly. The hprod of NLP at the starting point for a given vector is this thing, and if I subtract AD and LP, I'm gonna use the same starting point. It's gonna be close to 0. So it's not close enough, but it's close. For some reason, it's very large. This error is very large. I don't know why. Anyway, so it's close enough to 0. And here I can show the speed difference. X0 VHV. By the way, I just noticed that yeah, the epsilon is 10 to the minus 6, so I wasn't expecting this large, but where I'm not using, so one thing that I forgot, that is a mistake, I'm not using objective weight, so I should be using objective weight here and here. Though to be honest, this would go unnoticed for some time because we don't use the objective weight so much in our models. So here, comparing these two, so here, one of the reasons why our ADNLP is not recommended for second order, it is much slower here. It's 3 microseconds versus 29 nanoseconds. Okay, this is not much for our 10 variables model, but for something in the thousands, it will be very slow. And the reason is because we are using only forward diff, so our Hessian is dense. Whenever we can't make anything efficient, maybe the H-broad is a little bit more efficient, but even that is gonna use the derivative of a derivative and it's gonna be slow, so not recommended usually. And I can call here my trunk now. Same thing, I'm gonna print NLP again. I'm gonna reset my NLP. So this here is the output of our trunk method, and this here is the output of our NLP. It uses a little bit more evaluations, less gradient evaluations, and more H-broad evaluations because it uses it internally in the conjugate gradient. Okay. So another example in which I just define the new function H-broad exclamation and I call trunk and it works. Okay. Let's improve this a little bit more because now I want to call IPOpt. Can you compare DNLP with trunk? Let's do that. So here. So while it runs, I'm gonna prepare for the next one. So what I'm gonna do next, while it's running, is I'm gonna try to run IPOpt. IPOpt is the same objective here to solve the problem and the same function signature. The main difference being that it doesn't use the logger, so I'm gonna have to pass print level equals 0, which is a IPOpt argument. And here comparing the two, with our NLP is half the time as with ADNLP. So in this case, it made a lot of difference. It's that slower. That's always interesting to compare these things. Also notice that it's in the microseconds, sorry, and our our LBFGS was in the milliseconds. So trunk is much faster here. So you can feel the model's difference more accentuated. Do you have time to test it with a MathOp NLP model? I think I have. I just don't know if I don't have it installed, so let me install it. Well, let's run this first. Well, that was fast. So I'm gonna use ADNLP model. I'm gonna call model. I'm gonna define variables, which are I don't want to use X here. I know. Let's wrap. I can use a scope here. I never use the scope like this. So our jump model, or jump NLP, better name, is gonna be just in case I decide to change this. I see. I'm gonna sum xi, not here. I was hoping it was already copy pasted. Xi squared for I equals 1 to 3 to n minus 1. Objective minimize this sum. Okay, I think it's the same. And there is no constraints. There are no constraints, so I'm just gonna return math. Is it math opt NLP model? Yes. Let's see if this works. I forgot to use jump as well. So this is gonna fail because I don't have jump. Oh, it actually worked. Well, anyway, I'm just gonna add jump anyway. And the other error was that I don't have NL objective, because this is nonlinear. It's live benchmarking. Okay, so it worked. So I have jump NLP model here. I'm gonna move this. It's jump NLP. Jump NLP not defined because why not defined? Let me check that it's the return broke it. I'm not sure why. And there you go. The jump model is a little bit more efficient. Oh, I forgot to set a starting point. So my mistake, sorry about that. So that's maybe why it's so different for IP-opt. So I'm not being fair here. I'm not using a starting point. So this is I is divided by 2, divisible by 2. I love these live coding moments in which you find some error. So here the starting point was not being used, so it's wrong. And now it's correct. I'm actually still... There's still something wrong here. Oh, there's 2 errors in my jump model. I was skipping a whole variable. So actually this here, in which we have printed the model, which was saying 9, and I said it's probably not considering the linear derivatives, is wrong. This is considering the linear derivatives. So I made a mistake here, and now it's correct. So everything that I made for jump has to be remade, because it was not solving the same problem. So here, for the jump NLP model, it's actually much slower now than the manual. You write everything. This is more interesting. So if you can define your model manually, it's gonna be much faster than using a modeling language. Okay, it's not absurd, but it's considerably faster. Wow. So let's just do this last part before we go to problem 2. And this last part is I'm gonna try to use IP-opt. And of course this is gonna fail again. And this is gonna fail with a has structure not implemented. So here, has structure is where the things become a little bit more hectic. So all this abides by my way of working with these things, which is the easy way. And now becomes the hard way, which is when you're gonna work with the sparsity, with the Hessian matrix, and then you need to work with the sparsity pattern of that Hessian as well. So if this were optimization course, for instance, this will now get into the specifics. Before this, it will be introduction to optimization. So the first thing is has structure. Whose has structure, or what is has structure? And has structure is the structure of the Lagrangian Hessian in sparse coordinate format. NLP, rows, and calls. And I'm gonna need this right after has coord, which is the coordinates of the objective Hessian, in our case objective, not Lagrangian Hessian, in sparse coordinate format. Essentially, I have to compute the Hessian and pass it following this structure to vals, which is a vector of values. So this is gonna be a little bit I'm gonna say boring, but it's not the right word. It's gonna be a little bit slow. Okay, let me break this in a bunch of lines because it's not fitting the screen anymore. So first I have to define what's gonna be my Hessian, and I'm gonna look at the problem. I'm gonna look at the problem here, and I'm gonna write what's supposed to be in the comments, so I can just copy. So when I compute I'm gonna look only at the block 2 here. When I compute the derivative, I found this guy, and then this, and this. There's no 200. Okay, just my organization. So this is gonna be a block of my Hessian, okay? 2 minus 400 alpha plus 800 x1 square in the diagonal, the II position. 1 to the right and 1 below, I'm gonna have minus 400 xi. This is a symmetric matrix. And then I'm gonna have 200. However, I do not store the upper part of my Hessian, the upper triangle. I don't store. I actually have something in the ith row and ith column. I then have something in the I plus 1, however you say that, the row 1 plus I plus 1, and the column I, and then I have something at the row I plus 1 and column I plus 1, and a lot of these. And the values are gonna be this thing, then minus 400 xi, and then 200. So this is what I have to return. First I have to return these rows and calls. So well, let's compute how many of these guys there are first. So it's 3 times n by 2. 3 times n by 2. So 3 times 2, 6. Yeah, that's fine. So this is the number of non-zeros. So for each one of these, I'm gonna have 3i plus 1, 3i plus 2, and 3i plus 3, which actually gonna be 3i minus 2. So it's 3 minus 2, 1. Yep. And this is gonna be I. 3i minus 1 is gonna be I plus 1. And 3i is gonna be I as well. Okay. So I'm thinking if I should say this. Well, let's just check. As structure, rows is zeros 15, calls is zeros 15. Okay, I should have 1, 2, my n is 10, 10 times 2, 15, 1, 2, 10, and 5 at each, yeah, 15 non-zeros, that's correct. Has the structure NLP rows calls, NLP extended, Rosenbrock, forgot to say integer. And here it's trying to use more than it's given. I have 9 blocks. No, it's not 9 blocks. It's 5 blocks. It's correct here. 3i for when I is, oh, I have to say this. I changed the way I'm thinking in the middle of the process. It's not good. And here's another problem. So I have to skip 2. And I have, yeah, and I have to use I divided by 2. So when I is 1, this is gonna be 1. When I is 3, this is gonna be 2. This is correct. And now this should work. 1, 2, 2, 3, 4, 4, 5, 6, 6, 7, 8, 8, 9, 10, 10, 1, 1, 2, 3, 3, 4, 5, 5, 6, 7, 7, 8, and so on. Okay. My vals, I'm gonna just create a simple sparse matrix so I can test this. Rows, calls, and ones. So here, so we can see 1, 1, 2, 1, 1, I'm sorry, 1, 1, 1, 1, 1, 1, 1, 1, 1 in only the lower part of the Hessian. 5 blocks in the diagonal. This is working as expected. Second thing that we need is the has chord. Notice that the hardest part here, for me at least, is defining all these things that involves computing the gradient, the derivatives manually, and making sure the indexes are correct. So that's the hard part for me. So let me make sure that has chord. Yeah, has chord also has an objective. So here the same thing applies. I need to populate my vowels. And they are populated by this thing here. So first thing, this xi is gonna be xi, alpha is gonna be xi plus 1 minus xi squared, and that's it. This is supposed, just to make sure, I'm gonna write 2.0, so this is a float 64. Oh, actually I'm gonna leave this out, and I'm gonna assume that x has the correct type, and I'm gonna return vals, and again I forgot the objective weight. So there it is. I'm gonna call here a vals equals zeros, and I'm gonna call the Hess scored at NLP meta x0 vals. Yeah, that's correct. And this is the Hessian at that point. Notice that I'm saying a matrix of the sparse of this thing. Okay, so I'm gonna remove the matrix here so you can see. And if I call the Hessian, which I did not define, it's gonna fail because of something. What? Oh yeah, it's gonna fail because I have not defined this important part in the beginning. Here, the number of non-zeros in the Hessian. So the number of non-zeros in the Hessian is 3 times half of n. And I'm gonna assert that n can be divided by 2. Okay, I can actually say n should be divided by 2, otherwise throw, well, just error. I don't want to go fancy here. Error extended Rosenbrock, no autocomplete for me, is only defined for an even. So here you can see that the extended Rosenbrock now has 15 non-zeros in the Hessian. So when I call, where is it? Hessian, it's gonna create the number, the correct row call and vals vectors with the correct size, and then it's gonna return me the Hessian matrix. Okay, so for someone just trying to show how your method is implemented and he wants to call Hess directly, the internal API creates the sparsity structure and the coordinate structure for you. This, of course, will be much more expensive, or a little bit more expensive than this, especially because it's allocating. Okay, so you can always call it directly. IPOpt, of course, is defined using that internal structure. Maybe some printing, IPOpt. Okay, only a lot of printing. So IPOpt is using that structure internally. It uses a structure and chord. Okay, we can see that the output is the same. And let's just reset and print the output and the model. So here the solution is essentially the same, has some multiplying information that is not used. And here we use 45, 23 gradient evaluations. Notice that we forgot again to set increment on these things. So the structure is supposed to be called only once, so we do not have an increment for that. But the Hessian should be called a lot. So increment NLP Hess, and here again. Increment not defined. Okay, of course. I forgot to say NLP models increment. So I usually like to do my live coding without much preparation, and this is one example of that. So I computed the Hessian 21 times. I IP-opt, not me actually, probably needed 2 evaluations of the gradient outside the Hessian, outside the loop, and used the Hessian 21 times. Probably the first time and the last time. And 45 functional evaluations in the middle. Something like 2 for iteration. So let's go to this part in which we benchmark all models. Let me create a wrapper. Print level 0 for everyone. Sorry about that. So you can see here that IP-opt already solved it. The problems are in the milliseconds again, so it has a lot of things going on. And surprisingly, well, not very surprising actually, the jump model is the faster one for this case. So we make more allocations. As we said, we have, I need to copy paste this thing so I don't have to go all the way back. So we are always allocating here, so we allocate much more, and here as well. We can try decreasing it a little bit. It's not gonna be much, but you can try something like this. And something like this. It won't be much. And also we forgot to benchmark the function rows equals zeros int 15 calls zeros. Oh, the thing here is that they're gonna have different values. Sorry, I can't. Oh yeah, I forgot objective weight again. And there you go. It was much slower that time. Interesting. So here I'm not sure what I can compare, because the Hessian structure and Hessian coordinate are different. I'm not sure what I can compare, but I should be able to compare just the Hessian. It's not much, but it's honest work. So there you go. We improved a little bit. Okay, it was 6.8 or something. Not much again, but the number of allocations is essentially half of what it was. So one example. One thing that the jump model is doing that we are not doing, that makes some difference, is that not this part. So this part of the model, which is constant, is not, we don't need to recompute it. So it can be computed only once. So we need to know if it's the first time or not. And this is actually being computed every time. There's no efficient here, and this as well. So it can be a little bit more efficient in this part, for instance. Here we always compute this division, which we could be a little bit better as well. And since we are doing all this manually and jump already does it symbolically, it's gonna be faster. So that's why there's the need for the I forgot how it's called, but that whole graph system, graph coloring thing. So here this is gonna be very irregular because we're computing the hashing of these three models, and they are very different. They are implemented in very different ways. We are being faster even though we are allocating rows and calls, and so we are allocating the memory here. Has may be allocating the memory as well. That's a reason. And here it's the slowest one. It's using a dense hashing. Okay. So just to make sure, the hashing of our model is this one. The hashing of ADNLP model is this one, is dense. And the hashing of the jump NLP model is this one. This is not supposed to be. Oh, I forgot to set a starting point. So there you have it. Same thing, same speed, essentially nothing changed. We could compare, for instance, the Hess structure and the Hess chord for these two methods. We could use rows equals zeros int 15, calls and vals. So here it needs rows and calls, and in the chord you need x and vals. So this won't work for ADNLP, but it will work for jump NLP. So you can see here that our Hess structure, it still has one allocation somewhere, I'm not sure where. Hess structure for jump also has one allocation, and ours is faster. Defining everything manually is faster. And the value, the Hess chord, so I believe that jump already computed the Hess structure, and when I call Hess structure, it just passes it to my vectors, to my rows and calls. Yeah, I think it does that. So it's actually not computing anything here. The structure was already computed before. For the Hess chord, there is no allocation. We have 28 nanoseconds. And for jump, it has 2 allocation, but it's considerably slower. So this essentially sums up. If you want to have the most efficient, you have total experience, you want total control of your model, you can define it manually and use it. You have the other options. You can define it using ADNLP. If you try and it's slow, you can try jump, in which you're going to have to write using jump the formulas and the limitations of the vector value functions. And if that's not enough and you can't use the vector value functions, you can define it manually and just use ADNLP when needed, okay? So we could write something for instance, mixed using ADNLP sometimes and explicitly using the definitions that you have. And you can see here we ran this. Now that I fixed jump NLP, our model is a little bit faster, not much, than jump model. As I said, IPOpt is internally using a lot of things, so it's what dominates the time. Okay, this small difference here is negligible. So that's why, even though we are much faster for one evaluation, when you're considering the solution of the systems internally, that's nothing. Okay, so that's why you can test these things with slower models first. Okay, so this is the end of the first part of defining your own model. So what comes next? Next, we want to use constraints in our model. So the same thing that I did today, you're gonna do for the constraints. So here in the API, you can see which functions are used. Okay, so C of X, the Jacobian of X, and if you want second order, the Hessian of the Lagrangian. So you have cons or cons exclamation. This is the main one, cons exclamation. And for the Jacobian, since it's a matrix, you want Jack structure and Jack chord, okay? The same thing that I did for has structure and has chord, you're gonna do for the Jacobian. And the Hessian of the Lagrangian is essentially the same function, except that it now has a Lagrangian vector as well. So that's it. You have to implement possibly 3 functions for a second order method. You can also define jprod and jtransposeprod if you want a matrix-free method. Okay, so we're gonna create something for this in the next tutorial. So thanks for watching. Please like and subscribe, and follow me on Twitter and Twitch as well if you want to follow the live coding of these problems. I hope you enjoyed, and I'll see you next time.